So now let's think about an example, which is the OLS estimator. And in the case of OLS, the log likelihood function, it is not now it's not a log likelihood function anymore. So we are minimizing the least squared, the squared residual. This is the residual squared, and that replaces the log likelihood function. Still, we are going to denote it as L, so we have the first derivative and the second derivative in this form. So also you can check the dimension. The first derivative is k by 1. Second derivative is k by k. Now you may use the conditions to check the asymptotic normality. To prove the asymptotic normality, you can check 7 conditions. Like beta 0 is the unique minimizer, which was the identification result and was like it must be in the homework. And theta, the parameter space is compact, which is by an assumption. You need to additionally assume that the coefficient is bounded, and twice continuously differentiable, which is trivial because we know the function form, and also we differentiated twice, so it shows that twice continuously differentiable. And supremum, easy to show, and supremum of the second derivative also easy to show. And non-singularity of the second derivative can be argued by adding the full rank assumption. The full rank assumption implies that the expected value of the second derivative is invariable. And finally, the variance, the Fisher information matrix, need to be calculated using the derivatives. So you need this homoscedasticity assumption. Conditional variance equals to sigma squared. Anyhow, under this assumption, we can use this form. And then we have, like, from 6 and 7, you have omega and h, and applying the result, you have the asymptotic variance of this form. So the asymptotic variance is h inverse omega h inverse. Just apply the matrices. Then, as you can see, expected value of x prime inverse x prime inverse. So this is cancelled out this, and 2 inverse, 4, 2 inverse, they also cancelled out. So in the end, we only have sigma squared and 1 x prime inverse. This is exactly the variance you learned in the OLS chapter, which is straightforward. Now let's think about an estimation. So it is purely theory. So we can calculate. In this case, we can calculate the asymptotic variance by. So to calculate the asymptotic variance, first you have to calculate the expected value of x prime. It is easy. You can just calculate this using the sample mean of x prime. From the data, you can calculate average of x. So easy. And sigma squared can be calculated using the residuals. Once you estimate that result, then you use the residuals, and the standard the variance of the residuals is consistent estimator for sigma squared. Like this, you need to estimate the variance. Asymptotic variance is just a theoretical result, but it does not give. But what you need is a number, like whether the variance is like 0.1 or 0.2 or 100. So you need to have a specific concrete number, but it's the formula does not give you the number directly. Therefore, we have to think about estimating the variance. Estimation of the variance is, so we consider the general form again. We know that we need to estimate h and omega, and h and omega depend on the first and second derivatives. So the derivatives do not cause any problem. The log likelihood function is known. We know how to calculate the first and second derivatives. We can differentiate a known function, so it's not a problem. This step is not a problem, but the problem is arising from this. So the matrix H, so it must be it's typo. It should be theta 0, and this should be theta 0 again. So theta 0 is unknown. That is our problem. If you know the theta 0, then the population mean is easily estimated by the sample mean. So the expected value of the second derivative can be estimated by the sample average of the second derivative. Similarly, you can replace expected value with sample average. However, how can you handle theta 0? It is possible, it is feasible only when you know the value of theta 0. Of course, if you know theta 0, you don't need to estimate theta at all. So it is useless result. But a simple way to overcome that problem is, if theta 0 is not available, simply we are going to use an estimator for theta 0 again. So you estimate theta 0 by theta hat. That is what we are doing here. And use theta hat again at the place of theta 0. So we call this plug-in estimator. Then you replace theta 0 with theta hat, theta hat, theta hat. And then you can calculate the asymptotic variance. So h hat, omega hat, and calculate this. And then we can show that your variance estimator is a consistent estimator for the true asymptotic variance. So the variance can be estimated and needs to be estimated. Okay, that is it. This is how we analyze an estimator, especially the M estimator, extremum estimator, which is one of the most common, more general form of estimation. I hope it helps. So try, and in homework 3, you will apply the results in some examples. Okay. See you later.